Hi, I'm Jeff Groh and this is Calculus 1. Today we're going to talk about extrema. As with every new topic, we begin with some definitions. We say that a function f has an absolute maximum at C, lying within some set S, if the height at C is bigger than or equal to the height everywhere else for all x that are elements of the set S. Recall that an upside down A means for all, and a backwards capital E means there exists. If you have an absolute maximum being the highest point for the function within the set, what do we mean by absolute minimum? Clearly, the inequality just goes the other way, of course, for all x within the set S. One thing to point out about this particular pair of definitions is that we're not assuming strictly greater than at C, but greater than or equal to, which means there could be other points within the set S where the height is the same. So we're not precluding the possibility that the function peaks out at the same height at two different locations, nor are we precluding the possibility that the function has a whole interval of points at which it achieves that absolute maximum. By extremum, we mean either a maximum or a minimum. So we have three new words: maximum, minimum, and extremum, which includes either a maximum or a minimum, or both. If the function is constant, the maximum and the minimum are the same. One must learn the plural forms of these words. We have maxima, refers to more than one maximum. Minima and extrema. There's a well-known theorem that you need to know. It's called the extreme value theorem. It says that a continuous function defined on a closed and bounded set attains both its absolute maximum and its absolute minimum. We can rephrase this theorem in a slightly different way. Let's state the theorem in a slightly different way. Let f be continuous on some closed and bounded interval AB. Then there exists C1 and C2 lying within the interval AB, such that f of C1 is less than or equal to f of x for all x in AB. So we have an absolute min at C1, and f of C2 is bigger than or equal to f of x for all x in AB. So f has an absolute maximum at C2. We can call this m and this m, and you can see that the function values lie between the minimum value and the maximum value. Remember the hypotheses of the extreme value theorem. The function f must be continuous. Also, it must be defined on a set that is closed, and that set must be bounded. To see the necessity of all three of these conditions, suppose that we have a function that goes up to a certain point and then jumps down like this. Maybe defined halfway in between in the middle. This function does not achieve that maximum value. Where is that maximum? At which value of x? It seems like the maximum would fill this hole, but at that point you jump down. So there are points that get higher and higher, but there's no point that gives that upper bound, that maximum. The problem with this function is, of course, is that it's not continuous. The failure of continuity on a closed and bounded interval between A and B led to the failure of the conclusion of the extreme value theorem. No maximum and no minimum achieved on the set. Similarly, if the set is not closed, if you don't include a function value at A and B, you might not achieve the maximum or the minimum value on that set. The failure in this case is that the domain in which the function is defined is open and not closed. If the domain is not bounded, suppose this function tends to 0 but never quite reaches it, you might like to say the minimum is 0 but it never quite gets there. In this case, the set goes from A to infinity. Now I know we're using a rounded parenthesis around the infinity, and that's because infinity is not a point. The set is closed if it contains all of its boundary points. A is a boundary point, but infinity is not because it's not a point. So this set is still closed, it's just not bounded. The fact that the set is not bounded led to the failure for there to be a point that achieves the absolute minimum for this particular function. For such an important theorem as the extreme value theorem, we should probably prove this, but alas, it is too hard. Wait for a course in real analysis. Yes, we'll close our eyes and smile and move along. Move along. We won't do this one. Recall that a neighborhood of a point A in the set of real numbers is any open set in R that contains A. So for example, 2 is an element of the interval from 1 to 3, so 1 to 3, being an open interval, is a neighborhood of 2. Now, we're going to define a concept of a local maximum and local minimum. One could be a maximum relative to one's peers, relative to points nearby. You can have a maximum at A in some neighborhood around that point. Similarly, you can have a local minimum. Just because you have a local maximum some point doesn't mean that there's another place with a higher local maximum. But that's okay. We say that F has a local or relative maximum at x equals A if there is a neighborhood of A on which F has an absolute maximum. And similarly, if F has an absolute minimum on some neighborhood of A, then A is a local or relative minimum. Minimum relative to points nearby, that is. Can we abbreviate neighborhood by NBHD? This is a common mathematical abbreviation for the word neighborhood. There's another word we need to think about. Where do these extrema, these local extrema, occur? On the last graph, we saw some of these extrema might occur at places where the slope is 0, but those aren't the only possible locations. It could be that we have some kind of cusp. And if we have a cusp, we might have a maximum where there is no slope, maybe where the derivative is undefined. We're going to make a definition. We call x equals a critical point, or sometimes a critical number, because technically it doesn't have both an x and y coordinate, just an x coordinate. In calculus 3, these will be points. If, and technically there are 3 conditions, we need A to be in the domain of the function, and either f prime of A is 0, so the slope is 0, or f prime of A is undefined, or does not exist, one way or the other. These are going to be important places to look for these extrema, but it doesn't guarantee that we will have an extremum at a critical point. the curve y equals x cubed, has a derivative that is equal to 0 at x equals 0, and yet we don't have a local max or a local min at x equals 0 on the curve y equals x cubed. Nonetheless, we will prove something important about these critical points. The theorem is if f has a relative extremum at x equals a, then x equals a is a critical point of the function f. I want you to be careful to note the logical structure of this theorem. Extremum implies critical point. When we have a theorem with statement A implies statement B, the converse is B implies A. There are two other things you should be aware of. Not B implies not A is called the contrapositive. And not A implies not B is called the inverse. I want you to think about the logical structure of these statements. Let's suppose that statement A is, I am in Paris, and statement B is, I am in France. Then A implies B would be the statement, if I am in Paris, then I am in France. Let's suppose this is a true theorem, and we're not talking about Paris, Texas. The converse would be, if I am in France, then I am in Paris. But that's not necessarily a true theorem. So just because a theorem is true with implication in one direction, that doesn't mean the implication goes the other way. Think about the contrapositive. Remember, A was the statement, I am in Paris, and B is the statement, I am in France. If I am not in France, then I am not in Paris. Well, that's a true theorem. If the original theorem is true, it turns out that the contrapositive of a statement and the original implication are logically equivalent. You can prove mathematically that if you can demonstrate one to be true, then the other one must also be true. The inverse would be, if I am not in Paris, then I am not in France. And again, that would not be a true theorem. But it would be equivalent to the converse. The converse and the inverse are logically equivalent. A theorem and its contrapositive are logically equivalent. In this particular case, the converse is false. Just because you have a critical point, that does not mean that you have an extremum. But if you are at an extremum, that must be a critical point. This will narrow our field of searching for these extrema. If we can narrow things down to just critical points, we can examine the critical points and then determine which of those points are relative extrema. So, this theorem being so important, let's prove it. Without loss of generality, we're going to assume that you understand this acronym, which stands for without loss of generality. It's a perfectly standard abbreviation in mathematics. Suppose f has a local max at x equals c. What does it mean that it has a local max here? Then there exists an interval AB such that f of c is bigger than or equal to f of x for all x within this neighborhood AB. If f prime of c does not exist, then x equals c is a critical point. Suppose f prime of c exists. Then to show that x equals c is a critical point, we need to show that the derivative at c is 0. We're going to let x be an element of the interval from a to c, which means then that x is less than c, x minus c is less than 0. Note that f of x is less than or equal to f of c, and that implies f of x minus f of c is less than or equal to 0. It follows then that our difference quotient, f of x minus f of c over x minus c, is the quotient of a number that's less than or equal to 0 and a number that's strictly less than 0. Negative over negative is bigger than or equal to 0. And what is more, we can take the limit. We can take the limit as x approaches c from the left, because we're only analyzing what happens to the left of c on this part of the problem. We know that this limit exists because we assume that the function is differentiable at x equals c. That means that this limit must be f prime of c, and since all of the quotients were bigger than or equal to 0, we deduce that whatever the derivative is at c, it's bigger than or equal to 0. Alternatively, let x be an element of the interval from c to b so that x is bigger than c, which implies that x minus c is positive. We still have f of c is bigger than or equal to f of x, and that implies 0 is bigger than or equal to f of x minus f of c. So f of x minus f of c over x minus c is the ratio of something that's non-negative or non-positive. It's the ratio of something is the ratio of something non-positive, negative or 0, and something that is negative. You have to then get something that is less than or equal to 0. Taking the limit as x goes to c from the right of f of x minus f of c over x minus c is again, because the function is differentiable, f prime of c, and that must be less than or equal to 0. Now wait a minute. When we were on the other side, we had the derivative was bigger than or equal to 0. On this side, we have the derivative is less than or equal to 0. And it has to be both. And there's only one way it can be both, and that is the derivative must be 0. We deduce that the derivative at c must in fact be 0, and hence x equals c is a critical point. That completes this case. This case was the case where we assumed that the function has a local maximum at x equals c. The proof follows similarly if you have a local minimum, just the directions of the inequalities are reversed. So I'm just going to say similarly, if f has a local min at x equals c, then x equals c is a critical point of the function f, and that will be the end of the proof. The extreme value theorem tells us that a continuous function defined on a closed and bounded interval attains both its absolute min and its absolute max. Where might those occur? Clearly, the absolute maximum or the absolute minimum might occur at an endpoint of the interval or at a critical point. And that gives us a procedure. For finding absolute extrema. One, find all critical points on the closed and bounded interval AB. 2, evaluate f at all critical points and endpoints. 3, the largest value obtained is the absolute max. The smallest value obtained is the absolute min. It's a very simple procedure. So, for example, suppose my function is 3x to the fourth minus 4x cubed, and I'm constraining myself to the interval -2 to 2. I want to find the absolute extrema. So step number 1. Let's find the critical points. This function is differentiable everywhere, so we only need to find the locations where the derivative is equal to 0. The derivative is 12x cubed minus 12x squared. We can factor 12x squared out of that, leaving x minus 1. The critical points are 0 and 1. We'll evaluate on the next step f at the endpoints and the critical points. Evaluating at 0 is particularly easy. We get a height of 0 there. And at 1 is pretty easy too. 3 minus 4 is -1. At 2 to the fourth, we might more easily evaluate this if we factor an x cubed out. 3 times 2 is 6, minus 4 is 2, 2 times 8, 16, and at -2, 3 times -2 is -6, minus 4 is -10. -10 times -8 is +80. It follows then that the absolute minimum occurs at x equals 1 and has a height of -1, and the absolute max occurs at -2 and has a height of 80. The right way to express these answers may be as follows. f has an absolute max of 80 at x equals -2. F has an absolute min of -1 at x equals 1. Let's look at another example. How about 1 minus x to the 2/3 on the interval -1, 2. Step 1. Find the critical points. To find the critical points, we calculate the derivative. We get -2/3 x to the -1/3. We need to be careful about this negative exponent. Let's express our answer with a positive exponent by taking this x to the -1/3 and shoving it across the division symbol. We'll have a x to positive 1/3 in the denominator now. You can see where the critical points are. There are no critical points where the slope is equal to 0, but there is a place where the derivative is undefined, and that's x equals 0. That is in the domain of the function. Remember, there are 3 parts to our definition of critical point. Point in the domain where either the slope is 0 or the slope does not exist. Now, we evaluate the function at the endpoints and the critical points. At -1, you have the cube root of -1, which is -1, squared is +1. 1 minus 1 is 0. You evaluate at 0 and you get 1. At 2, you have 1 minus the cube root of 2 squared. That number will be negative. It follows then that we have an absolute max of 1 and an absolute min of 1 minus the cube root of 4. We'll state our answer as f has an absolute max on the interval -1 to 2 of 1 at x equals 0 and an absolute min of 1 minus the cube root of 4 at x equals 2. Let's consider the function f of x equals x minus the cosine of 2x and constrain ourselves to the interval 0 to 2 pi. We're doing this in order to force you to think about trigonometric functions. To find the critical points, calculate the derivative and get 1 minus 2 times negative sine of 2x. When we subtract a negative, we get a positive. This is differentiable everywhere. So the only kind of critical point that you can have is one where the derivative is 0. So we'll set the derivative equal to 0 and solve for x. We get the sine of 2x is -1 divided by 2. Sine is negative in quadrants 3 and 4. And so we're looking for angles in quadrants 3 and 4 where sine is -1/2. We get 2x could be, in quadrant 3, you'll have 7 pi over 6. Another one in quadrant 3, another way around, would be 2 pi plus 7 pi over 6. So we have 12 pi over 6 plus 7 pi over 6 is 19 pi over 6. Those are both in quadrant 3. In quadrant 4, you'll have 11 pi over 6, and if you add 2 pi to 11 pi over 6, you'll have 12 pi over 6 plus 11 pi over 6 is 23 pi over 6. But those are 2x values and not x values. To find x, we have to divide all of those by 2. We had to go twice around because if x is between 0 and 2 pi, then 2x is between 0 and 4 pi. It turns out, dividing everything in sight by 2, the critical points are 7 pi over 12, 19 pi over 12, 11 pi over 12, and 23 pi over 12. We need to evaluate the function f at all 4 of these critical points and at the endpoints. Evaluating at 0, cosine at 0 is 1. We'll end up with a function value of -1. F of 7 pi over 12, it'll be 7 pi over 12 minus 2 times 7 pi over 12 is 7 pi over 6. That 7 pi over 6 is in quadrant 3. Cosine is negative in quadrant 3. And so the value will be root 3 over 2. F of 19 pi over 12, we get 19 pi over 12. And again, we're in the same quadrant, it's just another time around. And so you get plus root 3 over 2. At 11 pi over 12, you get 11 pi over 12 minus 2 times 11 pi over 12 is 11 pi over 6, which is in quadrant 4, a positive quadrant for cosine, which means we'll still get a minus. The reference angle being pi over 6, you get root 3 over 2. At 23 pi over 12, you get 23 pi over 12, again minus root 3 over 2. How about f of 2 pi? 2 times 2 pi is 4 pi. Cosine of 4 pi is 1. So you get 2 pi minus 1. Which of these is biggest and which is smallest? Surely the function value at 19 pi over 12 is bigger than the function value at 7 pi over 12, and that's bigger than the function value at 0, so we can tell the value at 7 pi over 12 is neither a maximum or a minimum. You can check that the absolute max occurs at 19 pi over 12, and the absolute min occurs at 0. The highest building in the town where I live was built by the Anadarko Corporation. The building is 439 feet tall. Let's suppose that we throw a rock upwards at a rate of, let's say, 50 feet per second. The rock is going to go up and then down and maybe splash in the water in the pond below. Now, I want to know when the rock reaches its maximum height and what the maximum height of the rock is. To solve this problem, we'll use the height formula. Initial height plus initial velocity times time minus 1/2 acceleration times time squared. The units that we are using here are the English units of feet. In those units, g is 32 feet per seconds squared. The height formula is then the initial height, let's say 439 feet, plus the initial velocity, 50 feet per second, times the number of seconds that has elapsed, minus 1/2 times 32 times t squared. This will reach its maximum height when the speed is 0. When this rock ceases to go up, that's when it will go down. It'll go slower and slower and slower until it gets to a speed of 0 and then go down. The velocity is the rate of change of position, and that is 50 minus 32t. If we set the velocity equal to 0 and solve for time, we'll get 50 divided by 32 seconds. That is about 1.5625 seconds. I'm going to store this so that I can use it again. On my calculator, I store by pushing the store button and then alpha A. Note that t equals 50 seconds is a critical point of the height function, a place where the derivative was equal to 0. That's the place where we will reach that maximum height. Find the maximum height. To do that, we evaluate the function y at this critical point. So we'll have 439 plus 50 times that 50 seconds minus 16 times that 50 seconds squared. My calculator is giving me 478, and let's round that to the nearest foot, feet. That's as high as the rock went. Consider the function absolute value of x, which has a graph that looks like a great big V. This function is bigger than or equal to 0, and f of 0 equals 0, which means that the height 0 is the absolute minimum, and it occurs at x equals 0. It has no absolute maximum on the unbounded real line. What is the derivative of this function at 0? Well, there is no well-defined tangent line, as you can see. Let's calculate the one-sided derivatives at x equals 0. We'll calculate the limit as h goes to 0 from the right. This function is 0 at x equals 0. calculating the limit as h goes to 0 from the right, the function is the absolute value function. If h is a little bit positive, the absolute value does nothing, and so you end up with h divided by h and a limit of 1, which kind of makes sense because the slopes are all 1 on the right. On the other hand, if we take the limit as h goes to 0 from the left, a kind of left-sided derivative, again the function value is 0, and we're taking the limit as h goes to 0 from the function is the absolute value function. And again, if h is a little bit negative, the absolute value makes it positive over something with the same magnitude but opposite sign. The limit is -1, which makes a lot of sense because on the left, the slopes are all -1. Since the right-sided limit is 1 and the left-sided limit is -1, since those are different, the limit itself does not exist, which means f prime of 0 is undefined. Or does not exist as a limit. You can see then x equals 0 is a critical point because the derivative of the absolute value function does not exist there. It is also the location of the absolute minimum. Let's look at a function that you're very familiar with. The sine function will constrain ourselves to the interval 0 to 2 pi. The graph is, of course, one cycle of the sine function. From your experience, you know that the absolute maximum on this interval will occur at pi over 2 and have a height of 1. The absolute minimum will occur at 3 pi over 2 and have a height of -1. Let's see how our theory works out in this case. The derivative is cosine x. We'll set that equal to 0 and try to find the critical points. For the cosine function, cosine equals 0 at pi over 2 and 3 pi over 2. These are going to be critical points, then, of the sine function. If we evaluate our function at the endpoints and at the critical points, that should tell the tale about the absolute extrema on this closed and bounded interval. The height of the sine function at pi over 2 is 1, at 3 pi over 2 is -1, and at 2 pi you get a height of 0. So 1 is the absolute max, and -1 is the absolute min. We were guaranteed that these points existed on the interval 0 to 2 pi by the extreme value theorem. Let's look at one more example today. X over x squared plus 1. If you graph this function on your graphing calculator, you'll get something that looks like this. Where do these absolute extrema occur? Let's calculate the derivative and find out. The derivative of the top is 1 times the bottom minus the top times the derivative of the bottom over the bottom squared. The derivative is defined everywhere, so the critical points will have to occur where the derivative equals 0. We can multiply both sides by the denominator and cancel it out. We'll have 1, we'll have x squared minus 2x squared is minus x squared. This factors as a difference of squares, and so we get critical points x equals 1 and -1. What is the value of the function at 1? 1 over 2, we get 1/2. The maximum of this function, the absolute maximum is 1/2 and occurs at x equals 1. By symmetry, the absolute minimum will be -1/2 and occur at x equals -1.